5. How are we doing? Everybody good? All right. Max. What direction is the velocity of the mass at time 1? You got a 50-50 shot here because it's just up or down. How do you know?
Because the spring's tension.
No. Good try, but no. Anybody? Michael, what do you got?
It's going up because at time 2 the mass is higher up, so the velocity had to push it up there.
There we go.
Oh.
Okay, yeah, at time 2 it's going to be at a higher position, so the velocity at time 1 is upward. So I'm going to put a note on here, different color, velocity. I don't know what its value is, but it's up. Everybody good? Now that having been said, okay, Max, here's your chance. You ready?
Yes.
Tell us about the direction of velocity at time 3.
It's down.
Everybody good? Okay, and at time 5, Max?
It's up again.
It's back to up again. So times 1 and 5, all of the motion is the same. The displacement, the velocity, and the acceleration are exactly the same. Okay, times 1 and 3, they are mostly the same, but the velocities are opposites. Everybody okay? Any questions? Okay, Joanne, tell us one force acting on the mass at time 2.
The weight of the mass. Yeah.
How big?
Equal to the weight of the mass in Q1.
There we go. Hasn't changed. Good. I'd be worried if it had. There's weight, same as what we had before. So Amy, tell us about another force acting on the mass at time 2.
Force on the spring, I'm guessing, but now it's going to be less.
Why would it be less?
Because if you know more with, I need to okay.
Ring!
Less than the weight's moving down. And it's going right?
You have an issue here with your going instead of physicsy words. So, Amy, hold that into the spring. If you let go and it hits me, you're in big trouble here. Okay? So the spring is pretty stretched right now, right? Just like at time 1.
Not.
Now the spring is less stretched. In which case is it pulling harder, Amy? The one where it's more stretched. So is it pulling harder at time 1 or time 2?
No.
No, what's happening.
Time 1, time 2.
It's less stretched, okay.
Less stretched, so less force.
Yeah.
How are we doing?
Oh, Patrick, I think
Be careful, Patrick. You need to trip down the stairs, honey.
no. Right.
Okay, so at time 2, our spring force is itty bitty. And this will be true anytime the mass is above equilibrium. The spring will be less stretched, the spring force will be less than what it was at equilibrium, and weight is now winning. So Adrian, tell us about the net force at time 2. What direction does it point? Down, because weight's larger. Everybody okay? So now we have, and I can't give a value for it, but I can say the net force is downward. That having been said, Patrick, tell us about the acceleration at time 2. Going is not going to do it. We're not interested in going. We're interested in accelerating. Yeah. No.
No. All right.
No, definitely not.
I tried.
Try harder.
Accelerating down.
Why?
Because weight is winning, so it's pulling it down.
There we go, because weight is winning, so the net force is down. Remember, net force equals mass times acceleration. The net force is downward, then the acceleration has to be downward. So I'm going to use the same arrow I used for net force, for acceleration. That doesn't mean they're equal. Apples don't equal oranges. They're a different measurement quantity, right? But they are both downward, and that's all we really need from the arrow. Everybody doing all right? Any questions so far? Let's see here. If the mass were at the very top of its motion, Richard, if it had gotten all the way up to the highest point it's going to get to at time 2. Everybody keep in mind, we're making this a special case now. If that were the case, what would the velocity of the mass be?
Okay, so if it's up very top,
Mm-hmm.
should be 0.
It's going up, it's going up, it's going up slower, it's going up slower, it's going up slower, it's going down. What has to happen between going up and going down?
It's gotta stop.
Has to stop. So here we're going to
You got
get
this, Eric.
a note that velocity equals 0, but it only equals 0 when it's right at the top. Any other time it's above equilibrium. It will depend on whether it's gotten to the top yet or not. Everybody okay? All right. So one other note about this. Since it's above equilibrium, I'm going to note it this way. I'm going to note that S, the displacement, is upward. Everybody good? All right. Eric? What changes between time 2 and time 4? Let's ask this. What doesn't change between time 2 and time 4?
The weight.
The weight. Everybody good? The weight stays the same, but the spring force goes
Increase.
up because the spring is more stretched. The net force switches from down to up because now the spring force is winning. The acceleration switches from down to up because now the net force is up. Everybody okay? And finally, the displacement, instead of being up, is now
Down.
down. Everybody all right? Any questions about this? We're good? If at time 4 the mass is all the way at the bottom of its motion, the velocity will be
0.
0. Okay, Brandon. At time 2 and time 4, what's the relationship between the acceleration and the displacement?
If the acceleration vector points down, then the displacement is like up or positive, whatever you want to call it. And then whenever the acceleration vector points up, the displacement would be down or negative or whatever you want to call it.
Everybody good? Who did their reading? And you should recognize what Brandon just said. Simple harmonic motion, the acceleration and displacement are opposite and proportional. Look at what we have on the screen. At time 2, anytime the mass is above equilibrium, the displacement is up and the acceleration is down. The further the mass gets from equilibrium, the smaller the spring force will become, the larger the downward net force will become, and the larger the acceleration will become. One other way to say this, by the way, is not just to say that the acceleration and the displacement are opposite and proportional, but that the net force is opposite and proportional to the displacement. How are we doing with that? Leanne, did you catch that last part? Okay. Everybody got it? All right, because we're about to run out of time. So basically, those last two things, those are the defining characteristics of simple harmonic motion. And I'm just going to say this point blank. You have to know those. Those are definitions. Okay? And you have to be able to state it either in terms of acceleration or in terms of force. So whatever you do to call attention to stuff in your notes, smiley faces, hearty things, stars, whatever, highlighted around it, okay? That definition you have to know. Okay? Everybody good? Any questions about simple harmonic motion at this point? All right, we're almost done. Maybe I'll make it before the bell rings. There is one additional point I'd like to make before we leave for today, and that is the students worldwide do a really good job with simple harmonic motion problems as long as the mass is doing this. As soon as the mass switches to doing this, everybody's like, ah! What happened? It's going sideways. It can't do that. Well, of course it can.
Oh my god.
I'm wearing a mask.
Yeah.
I'm not sharing like other people.
Oh yeah, no, I don't care about other
Okay,
people.
okay.
I'm just
As
saying.
long as the spring can both push and pull, then the mass can bounce back and forth sideways. I promise the next test will include a mass moving sideways.
No.
What?
Oh, out of time. What's for homework? Data, please.